In BCD number system, the decimal numbers are represented from 0 to 9. To add two numbers in BCD, we are going to use binary addition rule. The gray code is also a non-weighted code and it is cyclic. Then we want to add the ones complement number with the minute. Hello to all, a warm welcome to my new session. I am Revati, Faculty, Department of Computer Science, Vidhyaashram, First Grade College, MYSURU. We are on the 5th session of Introduction to Number System. Moving further, in today's session, we are going to discuss BCD number and addition of BCD numbers. I repeat, in today's session, I am going to discuss BCD number system and addition of BCD numbers. Then I am going to discuss Xs3 code and gray code. Then I am going to discuss conversion between gray and binary code. Before going to start today's session, let me to recall the things what I discussed in the last session. In the last session, we discussed ones complement and twos complement. At the same time, how to perform addition by using ones complement method and twos complement method. At the same time, we discussed how to subtract the number by using ones complement method and twos complement method. But in today's session, I am going to discuss BCD number system and addition of BCD numbers. Moving forward, we are going to get binary coded decimal number, that is BCD number. So here BCD stands for binary coded decimal number. So here binary coded decimal number system is a system in which the decimal numbers are represented from 0 to 9. I repeat, in BCD number system, the decimal numbers are represented from 0 to 9. By using 4-bit. I repeat, the decimal numbers are represented from 0 to 9 by using 4-bit numbers. It is often called BCD number or binary coded decimal number. And each bit of BCD number has a positional weight. I repeat, each bit of BCD number system has a positional weight. The weights are assigned as per the position occupied by these bits. That means the weights are assigned for each bit based on their position. So the weight of the first position, so it is going to start from rightmost is 2 to the power 0, and the second one it is 2 to the power 2, and the next one 2 to the power 4, and the fourth one 2 to the power 3. That is 2 to the power 0 is always 1, then 2 to the power 1 equal to 2, 2 to the power 2 equal to 4, and 2 to the power 3 equal to 8. So binary numbers are also called 8421. I repeat, the BCD coded decimal numbers are also called 8421. So here, based on the position, the weights are assigned. Consider the example 1101. So what is the position of this bit? It is 0, then it is 1, this is 2, and this is 3. So based on the position, the weights are assigned. So the possible weights here is 1, 2, 4 and 8. So this BCD number is also called 8421. to 1. In the 4-bit BCD, it is possible to represent, or it is possible to reconfigure only 2 to the power 4. That means it is possible to rearrange or configure 16 characters. It is possible to configure only 16 characters. Hence, 6-bit BCD code was developed. So, initially we had 2 to the power 4. So, what is the possibility? We are going to get only 16 possible character. So, overcome the advantage of 2 to the power 4 BCD number, we are going to use 6-bit BCD code. That means here it is 2 to the power 6. Then what is the possible combination you are going to get? That is 64 character. That means in 6-bit BCD number system, it is possible to represent 64 characters. So this is the example. Consider the example. What is the example here? 537. Now I want to represent this 537 into BCD number. So we know that the BCD numbers are represented by using 4-bit and the range starts from 0 to 9. So to represent 5, I'm going to use 4-bit. What is the binary representation of 5? That is 5 divided by 2. 2 2s are 4, 1 remainder, 2 1s are 2, then 0 is remainder. So that is 101. So here it is BCD number. I want to use 4-bit. So to represent 5, I'm going to use 4-bit. Then another one, 3. So it is, what is the binary representation? What's the BCD representation here? 0 1 1 0. And what is the BCD representation of 7? That is 0 1 1. So hence I'm going to club all 3 bits together. So I am going to get, this is the final value. So in the given example, 537 is my decimal number. Now I want to convert this decimal number into BCD. So this is the actual conversion of BCD. Moving further, this is the example. This is the another example for BCD code. That means I have the decimal number, that is 96.42. Now I want to convert this decimal number into BCD. So what I will do, I'm going to write BCD code for individual digit. So first I'm going to write BCD representation for the decimal number 9. So what is the binary equivalent? It is 1001. So that is same as your BCD number. Then for 6, I'm going to use 4-bit. So 0110. For 4, it is BCD representation 0100. So these are the binary forms. First, I'm going to write the binary equivalent of the given decimal number, and I'm going to convert that binary number into BCD form. That means at the end, I'm going to club all the values together. So this is the example for decimal to BCD conversion. Moving further, this is the table gives the complete information about binary coded decimal number. What is the decimal number here? 0. So what's the binary equivalent? Same as 0. Then what about BCD number? It is also 0. Then 1. Once again BCD is 1. And the binary number is also 1. Then to represent decimal number 2 in binary, it is 10. Same in BCD. Then for 3, the binary representation here it is 11. The BCD representation here also 11. Then for 4, 10, here it is 100. That means The binary representation of 4 here is 100, and for BCD it is 100. And for 5, the binary representation 101 and BCD is 101. Then for 6 it is 110 and BCD it is 110. And for 7 it is 111 and for decimal, that is BCD, it is 110. Moving further, for 8 it is 1000. Here also it is 1000. And for 9 1001 and for BCD it is 1001. That means the binary representation and the BCD number representation is same only up to 0 to 9. From 10, the binary representation and the BCD representation both varies. So, what's the binary representation of decimal number 10? Here it is 1010. But whereas in BCD, I'm going to consider 10 or 2 different digits. Now I'm going to write the BCD number for these 2 digits. So 0, it is 4 zeros. For 1, 1, 0, 0, 0, 1. So just see this one. So it is, what is the representation? What is the BCD representation? For 10 it is 0, 0, 1 and 0, 0. Then what about 11? Once again, the binary representation here it is 1011, but whereas BCD, so I'm going to consider 2 separate digits. Then I'm going to write the BCD code for this digit. So this is 001. While writing, I'm going to write these 2 bits together. Then what is the 12? What is the binary representation of 12? It is 110, but where it is 001 and 0010. That means it is 12. First, I'm going to write the BCD for 1, it is 0001, and for 2, it is 0010. So, this is the BCD representation of 12. Then 13, what's the binary representation? It is 1101, whereas it is 001, 0011. So, for the decimal number 14, it is 110. Then what about BCD? It is 001 and 0110. That means for 1, I'm going to write the BCD representation. Then I'm going to write the BCD representation for 4. Then for 15, it is 41. Then what about BCD? First, I'm going to write BCD number for 1 and I'm going to write the binary representation of 5. Then I'm going to write both the bits together. This is the BCD conversion of the given decimal number. Moving further, let's see the rules for BCD addition. So here BCD is a numerical code and the rule for adding 2 BCD numbers is given below. What is the first rule? Add 2 numbers using rules of binary addition. That means to add 2 numbers in BCD, we are going to use binary addition rule. Then if the 4-bit sum is equal or less than 9, it is valid BCD number. That means whatever the sum you're going to get, if it is below, that means it is less than or equal to 9, then it is valid BCD number. Else, if the 4-bit sum is greater than 9, I repeat, whatever the sum you're going to get and the sum is greater than 9, then if a carry out of the group is generated, then it is invalid result. That means whatever the sum you're going to get, if that is greater than 9, then it is invalid result. Now add 6 to the 4-bit sum. Consider the example. I want to add two BCD numbers. These are the binary numbers. First, I'm going to write the decimal equivalent for this number. It is 9 and it is 4. After adding 9 plus 4, what is the answer? It is 13. So, in BCD numbers, it is possible to represent only 0 to 9. After 9, whatever the number we are going to get, that is invalid number. So, first I want to add two numbers by using binary addition. So, here 1, 0, I am going to get 1, 0, 0, it is 0, 0 plus 1, 1, 1 plus 0, it is 1. So, this is the binary representation of the number 13. Now, this is invalid number. So, I want to convert this number into BCD. For that, I am going to add 6. What I will do? I am going to add 6. Now, I am going to perform binary addition, that is 0, 1, 0 plus 1, it is 1, 0 plus 1, it is 1, then 1 plus 1, it is 0 and 1 carry, 1 plus 1, it is 0 and 1 carry. So, what I will do? I am going to group first BCD group. That means I am going to consider first 4 digit as my first BCD group and add the carry to the next 4-bit group. That means I am going to create another BCD group, that is the value, that is the carry value 0, 0, 0, 1. And at the end, what I will do? I am going to write first BCD group and second BCD group together, and this is my answer. So, I am going to repeat here. In the given problem, we have two binary numbers. So, first what I will do? I am going to convert these number into decimal. Then I am going to perform decimal addition. So, what is the value I got? It is 13. So, here whatever the value I got, it is not in valid state, because in BCD we have only 0 to 9 states. So, first what I will do here? First I am going to perform the binary addition of given number. Okay, whatever the result I got, that is the value, that is the summation of the given bit. So, this is equivalent to my sum of the digit. That means whatever the summation I performed by using decimal number. So, then I am going to add 6 to the actual summation. Then I am going to perform once again binary addition operation. Then I am going to group the bits separately. So, I am going to consider first 4 binary bits are my first BCD group, and I am going to create another BCD group with the value carry. So, this is the way you can able to perform BCD addition. Moving further, we are going to get Xs3 code. Then what is Xs3 code? It is a non-weighted BCD. I repeat, it is a non-weighted BCD code. So, how BCD codes are represented? By using 8421 code. Here, Xs code is derived from 8421 code by adding 0011. That means whatever the BCD number you have or whatever the binary number you have, you're going to add 3 for that number to generate Xs3 code. So, here Xs3 code is a sequential code, thus can also be used for performing arithmetic operation. That means by using Xs3 code, you can able to perform arithmetic operation. By using Xs code, they are self-complementing code. That means Xs3 codes are self-complementing code in nature. Therefore, subtraction by the method of complement addition is more direct in Xs3. That means Xs3, it is also written as Xs3. Like BCD, it also have 6 invalid states. That is 0, then 1, then 2, then 13, 14 and 15. In BCD code also, we are going to get invalid state, that is 0, 1, 2, 13, 14 and 15. Whereas in Xs3 code also we are going to get invalid state, that is 0, 1, 2, 13, 14 and 15. So how many states? It is 6 invalid states. The complements of the subtrahend. That means you want to take the complements of the subtrands. That means whenever you encountered invalid state, that time you want to take the complement, that is one's complement of the subtrahend. In Xs3 code, we are going to get 6 different invalid state. So first we want to take the ones complement of the subtrahend, then we want to add the ones complement number with the minute. I repeat, we want to add the complement number with the minute. If you get any carry, add the carry to its LSB, else take one's complement of the result, which will be negative. That means, so after adding, suppose if you got carry, then add that carry to the LSB, else take the one's complement of the result will be the negative. So moving further, we are going to get the relationship between decimal number, binary number and Xs3 code. So what is the decimal number we have? It is 0. Then what is the binary representation? It is 0, 0. For Xs3, that means to convert Xs3, I want to add 3. That is 1, 1, 0, 2, 0. So I'm going to get 0, 0, 1, 1. So the Xs3 representation equal to 0 is 0, 0, 3, 1, 1. That is 3. For 1, the Xs3 code is 4. For 2, it is 5. For 3, it is 12. So it varies. That means whatever the binary number you have, you want to add 3 for that. So for 2, what is the binary representation? It is 1, 0. So what I want to do, first I want to write this one into 4-bit form. Now I want to add 3 here. So 0 plus 1, it is 1. 1 plus 1, it is 0, 1 carry. So for 2, what is the BCD representation? It is 0, 1, 0, 1. So same answer what I got. For 3, what is the binary representation? It is 0, 0, 1, 1. And what is the Xs3 representation? It is 1, 1, 0, 0. So how to convert Xs3 code? That means first you are going to get binary number or decimal number. If you are going to get decimal number, then first you want to write the binary equivalent for the decimal number. Then you want to add 3 for that decimal number. So after adding 3 with the decimal number, whatever the value you are going to get, that is your Xs3 code. So consider the example 9. So what is the binary representation for 9? It is 1001. Now I want to add 3. So that is 0011. So after adding 3, what I will get? Once again, 0011. Here it is 001 and 1. This is the Xs3 code for the decimal number 9. So this is the Xs3 representation of a decimal number 9. Let's see the example. So this is the given number and it is in the form of decimal. Now I want to convert this number into Xs3. So what I will do? I'm going to write the numbers separately. So one digit I'm going to write. First I'll write the binary equivalent 101. Okay, here it is 0100. Here it is 1000. Now I am going to add 3. 0011 plus 0011. Here also I am going to add 0011. So it is 4. 5 plus 3, it is 8 representation, 8 binary representation. So 4 plus 3, that means for binary value 4, I'm going to add binary value 3, that is 3 plus 4, that is 7. So what is the binary representation of 7? That is 1101. Then for decimal number 8, what is the binary representation? That is 100. Now I want to add 3, that is 11. What is the binary representation of 11? That is 1011. So this is the way you can able to convert your decimal number to Xs3 notation. Moving further, we are going to get gray code. So a gray code is also a non-weighted code and is cyclic as well. That means the gray code is also a non-weighted code and it is cyclic. It is referred as cyclic because the successive code word in the code differ by only 1 bit position. That means it is called cyclic because the successive code word in this code differ by only 1 bit position, that is unit distance code. So whatever the difference you're going to get here, that is in the form of 1 bit position and it is called unit distance code and it is also in reflective nature. In many practical applications such as analog to digital conversion, unit distance codes are used. Here unit distance code is nothing but gray code. Then where you can able to use gray code, that is to convert analog to digital, you can able to use gray code. Let's see the conversion of binary code to gray code. So dear student, to perform binary code to gray code, you must know the truth table of XOR gate. So what is the truth table for XOR gate? For 0, 0, I'm going to get the output 0. For 0, 1, I'm going to get the output 1. For 1, 0, I'm going to get the output 1. And for 1, 1, I'm going to get the output 0. That means in wherever we are going to get the 2 bits are same value, then output is 0. See this bit. A is 0 and B is 0. Output is 0. Then what about 1, 1? Both the bits are same. So output is 0. See these 2 bits. Both the bits are varies. Then the output is 1. Moving further, this is the example for converting binary to gray. I repeat, this is the example for converting binary to gray. So what's the number here? It is 1001. That means the decimal number here it is 9. Now you want to convert this binary number to gray. That is gray code. So first what I will do, I'm going to write the value as it is. Okay, first initially what I will do, I'm going to copy the value as it is. Okay, then I'm going to add 1. That means I'm going to perform XOR operation. That is 1 plus 0. What is the value? That is 1. So once again I'm going to perform XOR operation with the next bit, that is 0 plus 0. That is, what is the value I'm going to get? It is 0. Then I have 0 XOR with 1. What is the value I'm going to get? It is 1. So just cross verify both the results are correct. To perform binary to gray code, first I want to copy the MSB bit as it is. Now I want to add the MSB bit with the next bit. That means I want to perform XOR operation. Okay, so what is the value? If both the bits are different in XOR, that is, I'm going to get the value, that is output 1. When I have both the bits same in XOR, I'm going to get the output 0. Then when I'm having the variation in the input bit, I'm going to get the output bit 1. So this is the conversion from the binary to gray code. Moving further, this is the another example for this is the way you can able to convert your decimal number to gray. That means first you want to convert your decimal number to binary, then perform XOR operation. Whatever the answer you're going to get after performing XOR operation, that is the gray code for your given problem. Then conversion of gray code to binary number. That means it is possible to convert the gray code to the binary number. So this is the given gray code that is represented by using G. Now I want to convert this gray code to binary. So how can I perform? That means this is the example used to indicate the conversion of gray to binary number. So what I will do? First I'm going to copy the last MSB bit. Now I'm going to perform the XOR operation with the copied MSB bit of binary to the next bit of gray code. That is 1 XOR with 1. What is the answer I'm going to get? I'm going to get 0. Now I'm going to XOR this 0 with this 0. So what is the answer I'm going to get? 0. I'm going to XOR this 0 with this 0. I'm going to get 0. I'm going to XOR this binary value 0 with the XOR with the gray value, that is I'm going to get 1. Now I'm going to XOR binary value 1 with the gray value 1. I'm going to get the result 0. So now I'm going to XOR 0 with 1. I'm going to get 1. If I'm going to XOR 1 with 0, I'm going to get the result 1. If I XOR 1 with 0, I'm going to get the value 1. That means whenever you're having 0, 0, you're going to get the value 0. 1, 0, it is 1. 1, 1, it is 0. And 0, 1, you're going to get the value 1. So you must know the XOR table truth. XOR table. That means XOR gate truth table. To perform the conversion of gray to binary, you must know the XOR gate truth table. Moving further, consider the another example. This is the gray code we have. Now I want to convert this gray code to binary. So what I will do? First, I'm going to copy the MSB bit of gray code as it is. Now I'm going to perform XOR operation with the binary number as well as gray code. So 1 is XORed with 0, I'm going to get 1. 1 is XORed with 1, I'm going to get the result 0. Here 0 is XORed with 0, I'm going to get 0. Then 0 is XORed with 1, I'm going to get 1. The 1 is XORed with 0, I'm going to get 1. The 1 is XORed with 1, I'm going to get 0. Then 0 is XORed with 0, I'm going to get 0. Then 0 is XORed with 1, I'm going to get 1. So this is the conversion of given gray code to the binary number. Moving on to the next session. In the next session, I'm going to deal with fixed point and floating point representation of numbers, then computer software. At the same time, I'm going to deal with types of software. In that, I'm going to discuss system software and application software. Dear student, in today's session, we studied the BCD code, then we studied Xs3 code, then we discussed gray code. That means how to convert binary to gray and gray to binary. Thank you for watching my session. Let's meet in the next session. Until then, take care. Thank you.